hope you can hear me. I not regularly use the microphone, and I love speaking loud, but I will now try to do my best with this. So today's talk is going to be about temporal recommendation, and I came from the Hungarian Academy of Sciences, where we had a research lab. It's an informatics laboratory. András Benzúr is the head of the lab, and we got like 20 people. To introduce temporal recommendation, what I wish to talk first about is the difference of today's recommender systems tasks and the Netflix prize. So there are three aspects that we generally focus on. The first is that today's recommender tasks are generally implicit recommendation tasks. Instead of ratings, generally we have only information on interactions between users and items in a given system. Second, recommender tasks are generally top-K recommendation tasks these days. Means you can also check this out on the figure that you have a given user, and for a given user you have to recommend a top list of given items. Third, today's recommender systems has to serve in very strongly temporal online environments. Think about news recommendation on Twitter when hashtags temporarily change day by day, how trends in social media change day by day. All right. To overcome these effects, first, I do not want to introduce you a model. Neither I want to introduce you an experiment, but first I want to introduce you a theoretical experimental setting in which we create our experiments. And hope this is also working or not. It works? Not really. It works? Okay, cool. We are researchers, and we need to work on timestamp implicit data sets to be able to offline simulate online research. Yeah, it's better now? Okay. Okay, I'm trying. Thank you. What we are doing is that we always process the events in the data in temporal order, and after each event, so we generate a stream-like evaluation, and after each event, first, we give for the recommender system the information that a given user is going to do something right now. And for this user, first we ask the recommender system to recommend a new top list, okay? Right after this top list, we evaluate the goodness of this top list, and then we give the information what kind of item was consumed by the user at that given time point, and we update our model. But right before this updating process, we do an evaluation part. And this evaluation is very natural, and you can see again on the figure. So for a given event, first the recommender system recommends a top list, and we have to evaluate somehow the goodness of this top list. This is what we're going to do in the upcoming slides. What we are doing, we simply check the actual ground truth, the consumed item by the user at that given time point. We check the position, the rank of this given item in our recommended top list. And we define a monotonically decreasing function called in the researcher recommender systems DCG for a given item and for a given rank. This can be seen by an equation up on the slide. So it's simply a monotonically decreasing function of the rank. If we had a predicted top list in which the actual item that the given user at a given time have consumed, then our recommendation is good. If it is not at the top but at the bottom, then our recommender is bad, and this metric is just going to be low. So higher is better in terms of DCG, and when you have a high DCG, then the item was at the beginning of the recommended top list. This evaluation setting is first very important for us because we were doing in the past context-aware, temporal context-aware recommendation. And anyone can understand that context can be highly temporal. There are two examples for that I'm going to show you in the upcoming slides. The first is social influence, the second is geolocation information. And to be able to investigate these effects and how well these effects can be used in case of a recommender system to improve the quality of your recommended top list, you need first a temporal experimental setting that I have just described for you. All right, the two examples. Yes.
Just to clarify, how big is this top list? And
Yes.
if the item was consumed by the user is not needed?
Very good question. Yeah, if you want, to be more applied, then I would say it can be a top list, its length equal to 10. And then if the item out of the top list, then you automatically set 0, this evaluation metric. However, in our experiments, we have done DCG at 100. The reason for this, because we just wanted a clear experimental setting when we could, as well as we can compare different models. In the upcoming slides, there's going to be DCG at 100. However, we always include in our measurements also results for DCG at 10. These are not going to be shown on the slides. Thank you. And something else on the evaluation is that with this setting, for each event, you have now a quality, how good your recommender was, and then we create from this like daily averages. So each day, we measure the average performance of the recommender system as time evolves. Getting back to the examples, so context examples where this evaluation can be important. First, we try to blend social influence in recommender systems. So we had a data set where we had a user-user social graph and a user-artist time series. So users have listened to different artists, and we wanted to recommend for the users new artists. How we have done this? On the figure, you can, again, check this out. So for a given user, like the orange one, if I want to recommend a new artist, the idea is I check her friends, and I check the very recent time series of her friends. And if I know from the past that she has a friend that she generally listens to, and now she has consumed something new, listened to a new artist, then we can recommend for the actual user the same artist. You can see the detailed mathematical explanation of our experiments in our paper. Here I just wish to give you the concept of this model. Here the concept is the probability of influence. So if I can, for two user pairs that are friends on a social network, somehow define and predict the probability of an upcoming interaction with a given artist. So the probability that there's a subsequent listening, they have consumed the same artist right after each other. And this was a result of influence between these friends. If I can predict this, then I can use this probability in recommender systems. To construct this probability, so we construct this probability from the probability of a subsequent listening between two users, and the probability of influence between the two users, given that there's going to be a subsequent scrabble. So both parts can be modeled. First is measured, actually, and then the first is modeled, and the second is then approximated from the data set in our experiments. And we could improve the performance of traditional matrix factorization models in online recommendation by blending them with social influence-related recommenders. The next example is hashtag recommendation on Twitter, when we have used geolocation information to improve the performance of traditional matrix recommender system models. Again, we had the temporal settings. Users post about different hashtags on Twitter, and that you can measure also the geolocation, the actual position of the user. And the task was then to somehow use this geolocation information to improve the models that we use for news recommendation for the users. This is what we have done. And on the figure, you can see the concept of this. We created by using geolocation, a hierarchical model for the different geolocations. So we created nodes for continents, countries, and cities. And we had this hierarchy in the system. And in each node, we have measures for a hashtag quantities like popularity and recency. And then when a given user, noted with orange in the figure, have logged into the system, we have checked her path now based on the geolocations. So she's like now in Hungary, and then it's in Budapest, and inside of Budapest she is on a given street. And then based on this hierarchical information, over this path, we have checked the popularity of different tweets, and then based on this, we have recommended for her new hashtags. So these were two examples how to blend context in a temporal settings in the research of recommender systems. This is great, and in all of our experiments, we used very popular model in the research of recommenders, so-called matrix factorization, as a baseline. In our recent experiments, we turn to investigate the simple matrix factorization model itself in a temporal setting. And I wish to talk in the second part of this talk about this in detail. First, a reminder of matrix factorization. Who is familiar with matrix factorization? I guess a lot of guys. Yes. Not that many. So I will introduce that very fast. You can see the concept of matrix factorization again on the figure. You have a very large gray matrix. This matrix is a so-called user item matrix, okay? And when in the past you know that there was an interaction between the given user and the given item, then you simply just check with mark 1, just check a mark 1 in this very sparse matrix, okay? So this is the data what you have. And in the future, what you want is to predict the future interactions in this matrix. So the unknown values of this matrix, noted with a question mark. And I can note that. Cool. This is the data what you have. Upon this, you create a model. Matrix factorization model is very simple. And this is noted with an orange dense matrix on the orange dense matrix on the left, and a blue dense matrix up there. You define for each user and for each item in your model a vector. And from the vectors, you construct a matrix P for the users and a matrix Q for the items. A given row of matrix P corresponds for a given user. It corresponds with, this is the corresponding vector for that given user. Similarly, for the items, you have a column. So for a given item, you have a vector here, and this is for item I then in this example. If you want to predict the future likelihood, how likely these two, this item and user are going to interact in the future, in your model, you simply compute the scalar product of these vectors. This is noted here, okay? If these vectors have the same direction, then this probability is high. If these vectors have completely different directions, then this probability is going to be low. Now comes the question that if I have this very large sparse matrix, how can I learn, these representations, these two dense matrices in my model, to use them for future prediction? In the research of recommender systems, there are two very popular learning optimization methods for this. They are called IALS, implicit ALS, and SGD. Next, I will show you a lot of SGD-related experiments. I just once going to emphasize IALS. So a few words in SGD without any kind of equation. Think about the following. You have observed that a given item has interacted now with a given user. And you want to learn from this information. What you do is the following. You compute first the scalar product of the two corresponding vectors and check whether you could predict this interaction with high probability or not. And if you observe that not, so your error was large and you couldn't predict this interaction, then you start to get closer these vectors, okay? This is the concept of SGD learning in case of matrix factorization. When you observe an interaction, you check the two vectors corresponding for this interaction and get the two vectors closer to each other. All right, yes, right after this, let us observe matrix factorization in non-stationary environments. So this is your model, and now I'm giving you a very temporal data set. What are the problems that you can tackle here? Check out the figure again. You have users noted with orange, and noted with lighter yellow, you have upcoming new users in the system that you have never seen before. So this can be a problem when new users come into the system that you have never seen before, and you cannot set up a proper vector for these guys. Second, this can, of course, happen with the items. And there's a third effect, that the preference of the users can change over time. So think about music listening. Depending on your mood, you listen to different music, and services like Spotify should recommend for you music based on your actual mood. So this is one effect that we should tackle during the learning process of a matrix factorization model. Third, I have a statement that you're going to see that consistent with our experiments, that you're not going to be able to see anything similar in case of the item vectors. So item vectors are typically static and stationary. If I have a track and I know that this is a classical music, it's just not going to change. Okay? So we have this user item matrix model where the user preferences can change. Both new users and item can get into the system. However, typically the item side is static and should not change over time. All right. Before explaining our experiments, I introduce you the data set with which what we have used in our experiment. This is the 30 million song music listening data set by the Crowder team. We have implicit timestamp music listening information here. For each record, we got a timestamp, a user, an artist, an album, and a track. We will investigate in our measurements temporal artist and track recommendations. So first I'm going to show you experiments in which we try to recommend new artists for a given user. Next, I will also show you experiments in which we recommend new tracks for a given user. In our toy data set, we have 50,000 users, 100,000 artists, and 500,000 tracks. Yes, this is it. And before the experiments, some more information on this data set. In this figure, I have shown for you the number of new users, tracks, and artists per day in this data. But you can see, observe that the y-axis is on log scale. You can observe that the number of new incoming artists disappear over time. However, the number of new incoming users and tracks is gonna do not drops and keeps over time. So there are a lot of new users and tracks that come into the system. However, the artists are new artists slowly disappear. This is reasonable, I guess. All right, getting back to now, let's construct online learning models with which we can learn matrix factorization on this data set. Here I list for you very simple four temporal learning methods that we're going to compare in our experiments. These are the code names, and I'm just going to detail this for you in the upcoming slides. First, I will compare a periodic batch learning method with a so-called simple online learning method. This is what you can see here. These are heavily used by, even in the industry and in the research community. We'll compare a so-called batch SGD and an online SGD. Observe first the gray line. So imagine a stream-like data where one by one you have incoming records, information, what users listen to in your system. And in case of a batch learning method, what people typically do is that create a weekly relearning method. So at the end of the first week, represented by the first small line, they gather all the information that they got in the first week, and in batch learning, by a lot of iteration over the dataset, they create a model. And then they use this for prediction in the next week. But they do not do any kind of learning during the second week. But then at the end of the second week, they gather all the information what they got back in the past, so information from the first and the second week. They learn their models again, and then they use this for prediction in the next upcoming week. And this just goes on week by week. We always forget the model, but relearn at the end of the week by using all the information from the past, a new matrix factorization model. We compare to this a very simple online learning method, we have seen that SGD iterates one by one on the data set. So why not do the following? Just one by one iterate once in temporal order in each record, okay? So this is going to be another algorithm, the same matrix factorization model, but with a different, very simple algorithm to learn. And here are the experiments. As I've told you, you can evaluate in a temporal setting these recommender models with DCG, and you can compute their average daily performance. So you see here a daily performance as the function of time for different recommender systems, and higher is better. You can observe that the simple online method that only just iterated once, a very simple one, highly outperforms a very much more sophisticated batch method that always relearned the model weekly. You can also see that the performance of the batch method drops over time. So right after the weekly relearning part, it has a strong performance, but then during the week, it loses its recency and the performance drops. So this is how online and batch methods can be compared. And in the research recommenders, people like creating statements like IALS is better than SGD or SGD is better than IALS. So in a batch setting, because IALS can be also only done in a batch setting, we compared these two experiments, even coming from two very different frameworks. So for SGD, we used our own framework, and for IALS, we used GraphLab Create, and we observe an identical performance. So I'm not saying that these two algorithms are the same, but I can say that even in this case, in this data set, in a temporal setting, these two algorithms just performed identically. But the online one, the online SGD, strongly outperformed the batch methods. The next experiment is the following. We done a very simple one. We simply shuffled our original data set. So we randomly shuffled the time series that we got, and then we measured similarly the performance of a batch and an online method in the shuffled time series. What we have seen is the performance of the online method dropped, and the performance of the batch method increased. This means that, yes, real-life data sets are temporal, they are non-stationary, and if your learning method, like an online SGD, if it can capture these temporal effects, then your recommender is going to be great. If not, then the performance is going to drop. Next, two kind of combination of the online and the batch world. The first is a batch and then online combination, where we created a very simple experiment. You can, again, see this in the figure. So observe like data from the very first 3 weeks. What we have done is that first we have relearned a batch method by iterating a lot of times over data set from the past at the end of the 3rd week. And then we have continued the learning of this model in an online setting with a simple online SGD by iterating just one by one over the records, then during the next week. At the end of the next week, so at the end of the 4th week, we've completely forgot this model, relearned again with the batch method a sophisticated matrix factorization model, and then continue the learning of that in the 5th week. So this is what we have done. We got a very surprising result that the combination just worked. This is surprising because the original batch method, noted with green, performs very bad compared to the online method. But as here we can see, the combination just works out. The explanation of this is the following. As I've told you, item vectors like to be stationary, and user vectors like to be non-stationary. So when you iterate a lot of times on a data set and you create a batch model, inside of a batch model, you will have a sophisticated representation of the item vectors, of the artist vectors. If you do not heavily change this during the next week, but learn the user preferences then with online SGD, online, in the upcoming week, you will be able to combine these methods in a temporal setting. Yes, this is explained also here in the slide. And the very last experiment is a sampling positive interactions from the past, again, to be able to combine these two words, the batch and the online words. Here, theoretically, we are not doing any kind of batch learning. We are doing an online learning method. We iterate on each record at once. This is the concept. And we're going to slightly change this by the following idea. When we learn in time for a given user and a given item at time t, we also observe the past of this given item. So the users that this item was also interacted with in the past. And we're going to randomly sample from these items by oversampling the very recent past. And we're just going to relearn on this record similarly in an online style like for the original record. So we randomly relearn records from the past. And we always update only the item vector. Okay, so we do not do anything with the user vector, but we get closer to the past the item vector. With this, we can simulate a batch-like learning for the item part of this matrix factorization model. And here you can see our results. For artist recommendation, this worked out because the number of new incoming artists dropped over time. However, for track recommendation, it heavily overperformed the previous batch online combination. Because in this case, in case of track recommendation, you have a lot of incoming new items. You have a lot of new incoming tracks. So you have to keep your algorithm online in order not to miss the performance that comes from the prompt learning of the present. So this is what we got. As a summary, we can say that the user item matrix can evolve in different ways. New users and items can appear. The item part is typically stationary. The user part can change over time. And different batch and online combinations can handle these effects. In our future work, we intend to investigate in details these effects and develop an algorithm that can automatically combine batch and online learning. And at the end, we wish to implement this as a part of the Streamline project in Flink. All right, thank you. Thanks. Train weekly. And at the beginning, the combination just going to drop the performance because at the very beginning of the time series, of course you have a lot of new users and items, so they just come continuously in. And in that case, online is great. The combination drops the performance because it combines batch user and item vectors that are overfitted on a very small data set at the beginning. We have two data mining challenges. One is the Rexis Challenge 2016. It's not late to participate. Check the web page out. We have a very interesting job recommendation data set in case of the Rexis Challenge. And the next one is the European Data Mining Conference, where we have a bank and geolocation related data. So if you are interested in, join to these data mining challenges. Thank you.